Have you ever stopped to wonder why a water molecule is bent, or how DNA gets that famous double helix shape? Well, it's definitely not random. Today, we're going to uncover the simple, elegant rules that give every single molecule its unique 3D structure. So let's dive right into the central mystery here. Molecules have these very specific, non-random shapes, which is kind of weird when you think about it. Why isn't water just a simple, straight line? Oxygen in the middle, hydrogens on either side. And the answer is, well, it's actually way cooler than you might think. Here's how we're going to crack this code. First, we'll start with the one simple rule that governs absolutely everything. Then we'll see what happens in a perfect world. And finally, we'll introduce a real troublemaker that breaks that perfection to create the shapes we see all around us. The answer to our mystery lies in one single, powerful idea: VSEPR theory. And I know, it looks like a jumble of letters, but trust me, this one concept is the key to unlocking pretty much all of molecular geometry. VSEPR stands for valence shell electron pair repulsion. Now, it sounds complicated, but the name literally tells you everything you need to know. It's all about one thing: electron pairs in an atom's outer shell pushing each other away. The best way to picture this is with balloons. Imagine tying a few balloons together at their knots. They don't just clump up, right? They naturally spread out to get as far apart from each other as possible. Well, electron pairs do the exact same thing. This simple need for personal space is the fundamental rule that dictates a molecule's final 3D shape. Okay, so what does this rule look like in a perfect world? Let's start with the simplest case: a central atom that's only surrounded by bonding pairs. That is, electrons that are busy connecting to other atoms. When all the electron pairs are identical bonding pairs, they push on each other with the exact same force. It's a perfect, balanced standoff. This results in these beautifully clean, symmetrical shapes with predictable angles. For example, methane forms a perfect tetrahedron, and boron trichloride forms a perfectly flat triangle. Simple. But things get way more interesting, and a whole lot more realistic, when a new character enters the scene: the lone pair. This is an electron pair that isn't bonding to another atom. It just belongs to the central atom. And well, it's a bit of a bully. So here's the crucial difference. A bonding pair is stretched between two atoms, so its negative charge is spread out. But a lone pair is held tightly by just one atom, making its charge way more compact and concentrated. This means lone pairs are way more repulsive. They take up more space and they shove everything else away much more forcefully. This leads to a really clear hierarchy of repulsion. The push between two lone pairs is the strongest force in the molecule, period. A lone pair pushing on a bond pair is the next strongest, and the weakest repulsion is between two regular bond pairs. This is the hierarchy that totally distorts a molecule's perfect shape. This repulsion hierarchy isn't just a cool fact, it's a predictive superpower. It allows chemists to look at a 2D drawing of a molecule and accurately predict its final 3D shape and its bond angles. It's amazing. And it boils down to this really simple logic. First, you count the lone pairs. Just remember, they're the biggest bullies, so their powerful push squeezes the other bonds closer together. So the result? As you add more lone pairs, the angles between the bonds get smaller and smaller. Let's see this in action with real examples. Check it out. Methane, 0 lone pairs, has that perfect tetrahedral angle of 109.5 degrees. Now swap one bond for a lone pair to get ammonia. That lone pair pushes down, shrinking the angle to 107 degrees. And finally, let's go back to our original question, water. It has 2 lone pairs. Their combined repulsion is even stronger, squeezing those hydrogen bonds all the way down to 104.5 degrees. And that's it. That's why water is bent. Now, for every great rule, there's always an exception. And while VSEPR theory is incredibly powerful, there are these rare cases where chemistry plays by a completely different set of rules. It's called Drago's rule. This special rule only applies if 3 very specific conditions are met. The central atom has to be a larger atom from the 3rd row of the periodic table or below. It must have at least 1 lone pair, and it has to be bonded to atoms with low electronegativity, meaning they don't pull on electrons very strongly. If you check all 3 of those boxes, something pretty weird happens. When Drago's rule applies, the atom basically gets lazy. It decides it's just not worth the energy to create the special blended orbitals that VSEPR theory assumes. Instead, it uses its basic p orbitals to form bonds, and those just happen to be naturally oriented at 90 degrees to each other. So for a molecule like phosphine, instead of the 107-degree angle VSEPR predicts, its actual angle is way closer to 90 degrees.
So you see, the bench shape of water is no accident. It's the direct result of two powerful lone pairs pushing everything else around. And that simple bend is what makes water a polar molecule, the universal solvent, the very foundation of life as we know it. It just brilliantly illustrates this profound idea that complex structures all around us are often governed by very simple, elegant underlying rules. It really makes you wonder, what other simple rules are hiding in plain sight, quietly shaping the entire